Residents of Minnesota, 1689. Current Minnesota fishing license.
89?
Yeah.
It looks pretty dark north of town here on the way over.
And nobody can hold a fishing rod for you if you're 90 years old.
Well, like I say, the storm I was looking at is like up to Pine Island area, going north, across north of the town.
I've been using, when I go to meetings like this, I've been using Evernote.
This afternoon?
Yeah.
Well, I suppose maybe
By the patrol.
Ferg 4321.
No, I haven't.
coming through at that time.
Neither did I.
You get a big,
You're limited to two
high,
devices.
low gradient.
Yeah, that's
you know,
kind of a
like
hardship,
it's gonna
but
be
I
low.
only use it on this
Wait,
now.
somehow I knew about Linden.
On my device.
This isn't any of the stuff that's from the Carolinas, you know, this is all west of that.
My laptop.
Right.
Talking to guys from Raleigh. Towns, you know, south and east.
Last time I was here is
Or
May
4
of
feet
2017.
Rain already.
By the way, coming down to see us next winter? We've been getting pictures from our neighbor across the street. Harold is parking in front of our gate all the time now.
She doesn't remember where it happened, doesn't remember where it happened.
Oh, that was a committee meeting.
I wonder if it helps or hurts with it. Wonder if it helps or hurts in that.
Well,
So you can't get apparently the buddy
If you're a foreign exchange student, you can get a fishing
neighbor on
license
the other
free.
side
Huh?
If you're a foreign exchange student,
Oh, yeah, he had an alcohol problem.
cleaned up a lot.
Saying he
Then the one across
up many a
the
time.
street said, no, he just pushed it back in the backyard.
Boundary water strip was pretty good.
Today, and sure enough, he did push it back in the backyard. And he-
what'd
I
you
take
do about
away-
being one person? What'd you do about being a person?
It's still
Another guy quit too, so
way,
he said, well, if we're only gonna have 5, then I'll back out.
Doesn't help when he said that he was.
We're trying to close on a house. and
Put the names on.
people minded
We
you
had
know, on the
4.
other side, telling him that he had
Andrew
to
and
pay
me,
an
and then
$800
2
fine.
guys from Marine.
Well, it's like a high school.
Stomping on
It would have been more fun with 6.
They weren't?
How's she like her little church?
boys.
Casa there.
Catholic school.
She's just
A different one. Well, all girls.
absolutely happy.
Just glad we weren't there.
Oh, they didn't know each other at all.
We used to drive by there all the time going to Welch.
Yeah.
Just
Took
because
his name off.
That
Took his
event
name
by
off of the
5 minutes.
press report. A far leftist rat.
It's
What I'd like to do is have,
the people are
Like me.
progressive in that
over and check in my place,
they
So I
they
can
put
honestly
on a
tell the
community meal once
sheriff that
a
I
month.
wanted to check
now.
my place, because I did give
Just a free meal, all comers.
and you can't get in because
And
that
they
dump truck is sitting
they
there.
did it last Wednesday, and they had 280 people there.
Something else worth trying.
Recent.
No wonder they're down to that.
Not yet, I think he gets around Thanksgiving, he'll be
And
there.
Paid off.
did you know that a tornado hit the church?
Yeah, I saw your Facebook. story.
Yeah.
Anyway,
And then there were neighbors that
Parking
got
in
hit a
front
lot
of
harder.
he-
And
so he's got a Winnebago parked in front
I
of
was in
his.
Chicago, but the people that were taking, so they took meals to every family that they knew had some damage. And they said they saw lots of tears. So that was probably good. But it's a typical
That was gonna be the last year. I don't think she could pick him
Uh,
up.
He's in a
rural church. In their hearts, they're Democrats, but they all identify as Republicans.
I think they're just trying to delay the hearings until after next Congress.
Oh, no, they think this.
maybe the 3rd or 4th week in October, we might go over and see Mike and Bob. Then we'll go up to see Trevor.
I wrote a letter to Obama Sunday.
Oh, yeah?
Well, I said, how do you connect with Obama? And they said, fill in this.
Got a major life
They only
challenge
give
right now.
you
Nope,
2,050 or 70 characters.
he's
I had to net it down.
3 roommates.
We got like 6% of those.
And he had to sign, they had all signed an agreement that there'll be no drinking and no smoking in the,
They did a
and all 3 of them do.
profile
And
of Hagedorn
Susan and
and
Glenn are saying,
the Democratic calendar, who I don't know.
All right, well, just a couple quick announcements before we get started. First of all, I'd like to welcome everyone back for for coming back after the summer. And I think actually the weather changed on us like today. So it was summer this morning, and now this afternoon and evening, it's now fall. So you are in the right place. One other kind of maybe brief announcement is next month, I had promised, I don't know if you remember last fall, but we had promised a machine learning workshop. I am not 100% certain that is going to occur. We had our presenter is out of the country until the second week in October. So he may or may not be prepared to do so that would be the third week, so he'd have a week to prepare himself. It may be a long flight to do the same. So just as a heads up that might not be happening, but don't worry, we'll find something else if it doesn't happen to put in its place. So keep us on your calendar, again, the third Monday of October. That's all I had kind of to start out with. Again, if you do have any other interesting speakers or topics that you'd like to have us promote to the larger audience, feel free to contact me or any of the other IEEE XCOM members. So with that, I'll let Ron introduce tonight's speaker. Thanks.
All right, well, thank you, Dave. And give a quick biography on Mats Heimdahl. Mats is the department head and professor of computer science and engineering at the University of Minnesota. He earned an MS in computer science and engineering from the Royal Institute of Technology in Stockholm, Sweden, and a Ph.D. in information and computer science from the University of California at Irvine. His research interests are in software engineering, safety critical systems, software safety, testing, requirements engineering, formal specification languages, and automated analysis of specifications. So with that, Mats, welcome. Thank you for coming too.
Well, thank you. Can you hear me? So let's see if I can get all the technology to work here. Yes, I can. Yes, so I'm Mats. I'm the Department of Computer Science at the University of Minnesota. I've been department head for 3 years. I barely know what I'm doing. And what we've been interested in for a long time in my group has been safety critical systems. That's where I started out, in safety and software. So I've been using this slide a lot when I'm teaching. And we've been working quite a bit with the avionics industry and with medical devices and space applications. So you can learn everything you ever wanted to know about engineering. You can learn from Dilbert. You know that, right? So I use this. So this is the goal for every engineer, is to retire without having caused any major catastrophe. And I used this for years, I swear. And then a student came and said, I'm misquoting Dilbert, because the original quote is that the goal of every engineer is to retire without getting blamed for, which kind of changes the whole dynamics here. But what we've been interested in has been various kinds of critical systems.
The guys at VW just about pulled that off.
Yeah, that's, well, the catastrophe was mostly for VW there, and of course the environment. But no, we've been interested in critical systems. And so it's been space applications, satellite applications, commercial aviation, medical devices, typically something that's regulated, because they really have to first pay attention for regulatory purposes and also for legal exposure. They really want to get things right. And I gave a talk when I first came here to Minnesota in 1996 up at Medtronic, and talked about what we were doing, and then I said, so if you adopt some of these techniques, you can develop better and safer systems. And the guy there, he said, we're not interested in that, which took me by surprise. He said, our systems are good enough and safe enough. We don't have a problem there, really. Where we do have a problem is that it's really, really expensive and takes a lot of time. So we want to develop systems faster and cheaper. right, without losing any quality. And that was a big change in the way I was thinking about these kinds of systems and this kind of development, because then the value proposition is not better anymore, it's faster and cheaper. So they were not interested in piling on more things to do in their development processes. They'd rather do less or do things that's more efficient. So that has guided a lot of what we've been doing the last many years. And you've probably seen some variation of a picture like this, the waterfall software development process or view of how you do things. So you have some ideas, you write requirements, design, implement, and the only thing you can do on the downslope here is really inspections of various kinds. Right? You can't really run your requirements, you can't run your design. You can start running your implementation, and then you put everything together and hopefully it goes into this unnamed pacemaker or an airplane or something else that might be critical, right? Now, of course, when you do this, you test things as you're piecing it together. We all do that. And now, of course, if you're, well, it might be some analysis. I don't know anyone using these static analysis tools, Clockwork, Coverty, Code Sonar. There are a whole bunch that can check for things like division by zero problems, null pointed dereference, null object dereferencing, those kinds of things. So some people are using those a little bit. Now, of course, if you're in a regulated environment, or it's safety critical, or you just really want to get things right, security is another application where you really want to get things right, you have to test the bejesus out of this thing, and it costs a lot of money, right? So there are all kinds of reasons why you test. You want to check for runtime errors. You want to check, are there requirements? So you want to do some validation testing. Are there requirements, right? All kinds of reasons. And it's very, very costly. So we want to try to reduce that. And what surfaced on the field here of software development tools and techniques, big time about 10, 15 years ago. What year is it now? 18? Almost 20 years ago, then around 2000. Was this notion of specification or model-based development, where you might have a model. So it's not that you write requirements in the traditional sense anymore. We're going to discuss that in more detail in a second. But you build a model. There are tools for this, like Simulink, Stateflow. If you're engineers, you probably use those, right? The SCADE is a French one. That's very, very good. And what are the IBM ones? Rhapsody. Right? So there are several of these tools that can allow you to build a model that's actually executable. So you can run it and visualize what's going on. You can use it as a prototype potentially. You can test it. And what I'm particularly interested in is if you can write down what you want that model to do. You can use tools to check the model and see, does it do that? And when you convince yourself that the model works, you push the magic button and you generate code. Right? That would be really nice if we could do that. And there are tools that can help us do this. I mentioned Simulink and Stateflow from MathWorks. Yeah, there are several of these, but you've seen some of these block diagrams, state machines, those kinds of things in the past, I'm sure. So now, if we can adopt this, the way we do software development will change a little bit. We will still have to get a good idea. We probably want to write requirements. But instead of going through the design phase and architecture and a lot of those things, we use one of these tools to try to come up with a model of how we want the software to behave. So we can capture our design in a very, very detailed way. And if the tools support it, you can generate code from that. Right? What you can also do, and we're going to look in more detail on this also, is you can take your requirements and write those down as what we would call, that's interesting, properties, right? Some way of formally capture what this requirement means. And then there are all kinds of tools that you can use to double check this. That's my model, do what the requirement said it was going to do. Right? And when you convince yourself that the model implements the requirements, you push the button, you get code. And the thinking here was that you would do a lot of analysis in this domain. You would do some testing of these specifications and models in this domain. And then, as you're generating the code and integrating things, you do some integration testing and system testing. Anyone see a big thing that's missing now? From this? Ideally, there's no testing attached to the implementation anymore. Right? The idea here being, let's beat the bejeebus out of this thing, right? And then these are the requirements, and if we can generate code, and we trust the code generator, the code is going to do what the requirement said it was going to do. So we don't need to test these. We can integrate it right on the airplane or in the pacemaker and do the integration testing and system testing, and then we're good. That's not a particularly good idea, right? I think. First, we can't trust the code generators, and secondly, it used to be all kinds of testing down here, and now you can't eliminate it, it just moves, right? If you can generate code from something, it's just an alternate implementation, really, in a more domain-specific, more suitable language. So this was a big selling point or marketing point of some of these techniques once upon a time, that you can eliminate unit testing. You just build these models, their requirements, by definition, they're correct when you validated the requirements. And then you generate code, and by definition, that code is correct, so you don't need to test it. Right? That was, of course, utter nonsense. And we'll look a little bit at that also in a second. Right? So the testing doesn't go away. It just moves. So we'll talk about how you save money doing this. So what we want to do is to make sure we get this model right. As we're going through this, we want to get it right, so with the code that we generate, or we can derive the code. There's nothing that tells you have to use a code generator. In fact, some companies don't trust the code generator, so they have Bob or somebody take these models and code it up themselves, right? And how that is going to save you money, we'll get back to that too. But we want to get the models right, so we want to do a lot of analysis, and we might want to do a lot of tests. And we've been working on this for, I don't know, since I started, so 20 some odd years. What I want to talk about today, though, is really some about this and how these three things relate to each other and how they fit together. And so you saw some of these models. You can write simulating state flow, other kinds of things. Requirements, I don't know if this looks familiar. This is from a project we did with Rockwell Collins down in Cedar Rapids, funded by NASA largely in Rockwell Collins. But they have a lot of requirements that looks like this, right? So this is a flight guidance system. You have two of those in the cockpit, one for the pilot, one for the co-pilot. And one is active and the other one is in a slave configuration. So if this side is active, that means my flight guidance system is active. And the mode enunciations, which are the little twiddly things on the flight display that tells you to climb and descend and so on. The mode enunciations are off. The mode enunciations shall be turned on when the on-side flight director is turned on. So when you turn on the flight director, you push that button, these things have to pop up on the display. Does that look familiar requirements-wise? Typical English language, natural language shall requirements. The system shall do this or must do this. They have a whole bunch of these, I mean hundreds of these things when it comes to their flight guidance system. Now the big question is, of course, does our system do this? So what happened in this project is we built models of this system, and then they took these requirements and formalized them. So here's the same requirement again. This is pulled from doors, I think we used to keep this, keep track of all of this. And then you can write down, and don't get turned off by the syntax here because it is awful. But this is something called a temporal logic. So what it says is AG means always globally. So it shall do this, always. If the mode enunciations are on and not on-side flight directors, that little not thing there, the exclamation point, on-side flight directors are on, that implies that AX means in the next step. So in the next time step. This side better be active and the on-side, and if this side is active and the flight director is on, then the mode enunciation shall be turned on. So you can, it's almost a one-to-one translation from this into this, although it's a really ugly syntax. No normal human should have to deal with that, but this was a research project. Right. What does this do for you? Well, now you can take these tools. They're called model checkers. This is a very active area of research, and it really got a breakthrough in the mid-'80s, not in software engineering, but in hardware. right? So Synopsys and Cadence in particular were leaders on this for their verification of their VHDL models, right? And analyzing hardware is pretty easy because hardware is all big and complex. It's pretty simple because all you have are AND gates and OR gates and Boolean. The data types are really simple. They're all Boolean, right? So it turns out that analysis can be done quite effectively. And if you do, so this is I should have had, I don't know what happened to my credit to this. This is not my slide. This is Steve Miller. He was at Rockwell Collins. He used this to explain what they're doing to their management. So testing, he said, that's like searching for bugs with a little flashlight. You shine a little here, 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 and you shine a little there, and if you're lucky, you find a bug. Right? These model checkers, and there's a lot of paths, a lot of inputs to explore, of course. These model checkers, they do something very different. They don't run the system, they analyze the system, and they do it exhaustively. So he viewed that as having a big lighthouse, shining light on everything. And if there's a bug in there, you will find it. Right? Now there's a big caveat to that because these tools only look for what you ask them to look for. So if it's really safety critical that this signal and this signal are not high at the same time, you can assert that and say, it's always globally the case that these two are not high at the same time. Feed it to the tool and it comes back and says, yep, that's true. It doesn't mean the system is doing anything else useful. Right? The only thing we know is it's not doing something that bad thing. Whatever else it's doing, we have no idea. We have to ask more questions, add more requirements, add more properties. Right? Anyone tried any of these tools? So Simulink has a very nice tool I call Simulink Design Verifier that, if used correctly, is quite good. Right? When we putzed around with this 10, 15, 20 years ago, there weren't that many good tools out there, and you still have to be reasonably knowledgeable to use them. Otherwise, they just sort of grind to a halt. But this is how these tools work, and how it works is really this is you. This is your model that you built using Simulink, Stateflow, some language. I mean, it could be a C program too for some of these tools. But it's a model that you built. And you're interested in, does it do X? So what we do then is we write down what this X is somehow, right? We translate that to the input language of this model checker that we're going to use. We used to use one called SMV. There are dozens of these, not maybe dozens, well, dozens, maybe half a dozen that's really good out there now. You take your model and you translate that to the input language of these tools, and then you give it to the tool and push the button, and it will grind away. And then it will come back and says, yep. Well, maybe it'll come back and say, yeah. It will say, yes, this property is true in this model, right? And it's a proof, it's guaranteed that this is the case. Now, of course, this might not happen all the time. Sometimes it comes back and says, no, this property is not true. And the nice thing with this is that then it will also produce what we call a counterexample. So it will say, nope, this is not true. And here's a test case that will demonstrate how you falsify this thing. So in essence, it's saying, yep, I found a bug. Here's a test case that will demonstrate that it is a bug. And then you can take that, run it, and try to fix your model, right? The danger of this, well, there are lots of dangers, and we're going to come back to that also. This is kind of what this talk is about, is that it comes back and says, yes, but the question I always ask myself, it happened to me a lot, actually. So when I started out, I did a little happy dance because, oh, my model does what I said my properties were going to do. Woohoo, everything works. It turns out that most of the properties I wrote were nonsense. Right, so there were properties that were always true, for example. So it didn't matter what model you had. The tool would always come back and say, yep, those properties are true. Right, so the risk you're running here is that this is wrong, and this is wrong, and the tool catches nothing because they're both wrong in the same way. Right, so just because this pans out, you can't declare victory and go home, and we'll talk more about that in a second too. So what's the value proposition of doing something like this? Because in the old days, or in the old way of doing requirements, and you would write requirements, you would design, right? You would implement, design, implement, and then you start. Now, you're asking me to do, I'm asking you to do this, and this is a hell of a lot of work. How can that possibly save you money? Which is a good question. It's preciously little data available to, I mean, Dick cares about data, a lot of process people care about data, but it's really hard to come about. But anecdotally, right, so Rockwell Collins, they did a project with this, and they adopted sort of this way of doing things with simulating state flow because that's what Boeing mandated. There were some tools that we had developed that they adopted in-house, and they did this. Then they hand-coded from this model the implementation. This was for the display system at the new Boeing, what's that, 787 Dreamliner? And it worked smashingly well. They didn't take any credit for this. They just did this in addition. They went through all the steps they had to go through, plus developing these models and all these properties and do all this checking. And yet they saved money. And how they did that was by, after they hand-coded the code, it went through testing without any rework. Because they got all the stuff worked out up here. So by the time they got the code and the expensive testing that they had to do, there were no defects. Right? And that saved an enormous amount of money. So yes, it was probably more expensive to get all of this done, but they saved that tenfold in lack of rework, right? Because that's very, very, very costly. So that's how you would save money, by getting your requirements right. Right? And I always said, I think bad requirements, they're the source of all evil. Right? That's where software development projects fail. I mean, you have crappy requirements, your testing falls apart, your development efforts fall apart, everything falls apart if you don't have decent requirements or good understanding of what you really need to do. Feel free to ask questions and interrupt me, by the way, if you feel like it. So what does this have to do with what I was going to talk about today? Well, we've been doing things for many, many years with various systems. And when I was a grad student, when dinosaurs roamed, we worked on a system called TCAS, Traffic Alert and Collision Avoidance System. It's on all commercial air carriers now, and I think they might sell it for smaller planes also. But it essentially is a system where you have, anyone a pilot? No? Because I didn't know this before I started working on TCAS, that the only way pilots could figure out who was flying around them was to look out the window. Right? Air traffic control just told them, yep, that altitude, that direction, go. They had no radar, they had nothing on the plane. They just looked out the window, nobody's there. If I want to turn, better check that nobody's there. Now there was some mishaps in the mid-'80s. It was a mid-air collision in Cerritos, California. So they decided to put these things on airplanes. And what they did was they put directional antennas on top and directional antennas at the bottom that tracked aircraft, that fed it into a TCAS computer that was extrapolating all these paths, including the path of your own plane, and trying to figure out, are we going to run into each other sometime in the near future here, and let the pilot know if it was up or down, climb or descend. There's a little voice going, it wasn't quite this violent, but it was a little voice going off in the cockpit saying, climb, 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 and the primary flight display lit up and showed you with a airspeed indicator how much you should climb or how much you should descend. They had horrendous problems with the requirements back then. This was in the mid-'90s, late 80s, early 90s. Tremendous problems with the requirements. So they asked our research group, or Nancy Levis's research group, where I was a student, to come up with better requirements. And we built models. Not using simulating a state flow. They didn't really have these tools back then. But we came up with our own notation. But we built a model of how this should work. And then I knew how to write requirements. You don't write them in English language. You build a freaking model. That's what you do. It explains what the system is supposed to be doing. Case closed. Bada bing. We're done. So now I knew how to do things. Right? Then we got involved with this Rockwell Collins project that I just showed you. flight guidance system and other flight guidance systems. There's mode logic, control laws, they communicate with each other, they're connected to all kinds of junk around it. And in this project, this is when we started using these model checkers. And we started to write down these properties, right? If you engage the flight director, then the flight guidance cues must come on. And then we were interested, does the model do that? And then it became clear to me that the model is not the requirements, right? These properties that we write down, that's really the requirements, right? That's what the model shall be doing. It does what it does, but what should it be doing? That's what we want to try to capture. So that's what we did in this project, and then I knew what requirements were. It's not the model, it's the properties, right? Then we started looking at a different system, which was a GPCA, generic patient-controlled something pump. And there we ran into all kinds of problems trying to build models and write requirements, because we didn't really know. It was very hard to figure out where does the pump begin and the environment begin, and what's the interface. For example, are the needles and hoses and other things that go with the pump, are they part of the pump? Or are they not part of the pump? When we're going to write requirements, what do we write about? And the requirements that we got for these kinds of pumps were all over the map. Some of them talked about you can't do an overinfusion in the patient, which really talks about the patient. Other requirements might talk about the pump that's embedded in here. It says the pump stroke has to end on an upward stroke. And you go, why? Turns out they must have had a free flow problem, so the drug was just flowing through this thing because they stopped the pump at the wrong place. So they added the requirements. So some requirements talked about really internal implementation details of the pump. Other requirements talked about the patient, and that's not good. You want your requirements to talk about the same domain. So we got utterly confused again, so I think I'm back to square one now, really. I really don't know what I'm doing. But here, I thought I knew what I did. Here, I thought I knew what the answer was. Now I'm not sure at all anymore. And this has led us, me to this observation, that you can write requirements in three different ways, right? You can do natural language. You've seen that. The mode analyzation shall be turned on, blah, 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 right? So that's one way of doing it. You can do it in a formalized way. We looked at that very briefly. Same requirement, but written in this god-awful logic, computational tree logic, but you could clean this up with some surface syntax and it might actually look palatable to people to write in this way. So that we can do, or we can build models, right? This happens to be a model from the infusion pump, but not from the flight guidance system, because we didn't do the flight guidance system in state flow. This is a state flow model. You could argue that this captures the required behavior of our system, right? So there's really three different ways you could try to capture requirements. I was a big believer in this way 20 years ago. Then I was a big believer in this 5-10 years ago. And what I've come to conclude in those projects was that it doesn't matter what the heck you do, this is going to be wrong, right? It's just, they're going to be wrong. And unfortunately, these are also going to be wrong because we're just not going to get it right. And of course, these models are also going to be grossly wrong. So does that mean that we're, I don't know what the technical term is, but screwed? And to some degree, yes. If we go with this, it's going to be wrong. If we go with this, it's going to be wrong. And if we try to write down things only this way, it's going to be really, really wrong, I've discovered, right? So we need to do something with all of this. And that's really where we come back to the picture I showed a little earlier, that you're going to write down things in natural language. You're never going to get rid of that. If people say you can formalize everything, use formal methods, they're lying. You can't, right? They're not very good communications tools. People like language. And you can inspect those. And this is from an NASA workshop I was at recently. It just happens that the organizer looked exactly like that, so I had to use that picture. Except for the white coat, but besides that. But then you can take these natural language requirements and build yourself a model that you think does what the requirements said it should do. Right? And you can use Simulink, Stateful, there are all kinds of tools that you can use here. And it's kind of nice because you can inspect it, you can run these verification tools to check for certain things, like does it have any conflicting transitions? Are there any deadlocks in here? There are also the generic properties you can check for in these kinds of systems. Then, if you also capture these requirements or properties, and now I wrote declarative and synchronous with service, there are different ways of capturing these properties, but you really derive it from the requirements. You can inspect, analyze, and check these properties too, and then you use tools to double check these with each other. Right? So now you can run verification, these tools I talked about, model checkers, or you can just run this model and use these properties as your test oracle. Right? So that's another way of using these properties. And now you have really 3 ways of describing this, and I believe you need all 3 of them if you're going to go this route. Because this is going to be wrong, this is going to be wrong, and that is going to be wrong. Right? And by checking them against each other, hopefully you can go somewhere good. And that would look something like this. You have this is what my system ought to do. This is acceptable behaviors. Right? This is acceptable from our system. We don't know what this is. Right? This is just, if the system does this, it's okay. This is really unknowable to some degree. Right? So we don't know what this is, but this is the right thing to do for the system. So anything that falls inside this blue block or blue circle is okay. Right? Then we write down formal requirements, English language requirements that we might formalize. They would be here. Apparently we screwed up a bit here because this is outside of what's acceptable, right? We might build models. Models are typically more restrictive than the requirements. Typically, you write requirements. There are several ways of meeting those requirements, and you pick one when you design it and implement it. So the model is typically a little more restrictive than the formal requirements. And here we screwed up, so our model is wrong, right? It doesn't do what it's supposed to be doing. So now there are interesting things when we run this or run the analysis. So for example, here, right, here the model overlaps with the requirements and it all does what it's supposed to be doing. So if you run the verification, it says, yep, the model implements the requirements in this area. That's a good thing, right? We built the right thing. Then we have other areas here where the requirements and the model don't agree with each other, but they're both okay, right? That can happen. That the implementation is doing something, the requirements is doing something, they don't agree with each other, but they're both okay. Right? We could have picked either behavior, that's fine. Just rewrite the requirements so it matches or change the code so it matches the requirements. Either way would have worked. And then of course we have these areas where the requirements do not agree with the behavior of the model, and it's outside of what is correct, and this is a good thing to catch, of course, when we double check our requirements with the code. We look at it and say, oh, no, they don't agree with each other, and this just looks effed up. This is not right. Let's fix it. This area, of course, is very sinister because here is where the requirements agree with the code or the model, but they're both wrong, right? So now if we use these tools, we can run into scenarios kind of like this. We run the analysis, and it points out to us that here you have a problem, and it gives us a test case that we run. We look at it and say, yeah, that's not right. Let's fix our model. So we fix our model. We didn't fix the problem. I didn't move it far enough. But we run the analysis again, and we find another problem. And we look at it and say, let's fix it. So we fix it. Right? And now the model agrees with the requirements. And we call it a day. Right? Which is a bad scenario because down here, we're wrong. Both of them are wrong, right? What typically happens is something a little different than that. Is you run the analysis and you find out the model doesn't meet the requirements. Now it turns out that it doesn't matter. The model is okay, but we still change it a bit, right? So now we hope it meets the requirements. We run analysis or test it again. It doesn't meet the requirements, so this time, though, we decide that the model is actually right. So let's change the requirements. Right? And that happens surprisingly often when you do this. You realize that we built this model and it's actually doing what we want to do. It's just our requirements were crappy. And how come you can build a correct model or a model that does what we want from bad requirements? I'm sure that has happened in your organizations all the time. Why does that happen? Not by magic. I mean, you have good engineers, good programming people. They built 3 of these before. They go, this is what you should do. I don't care what the requirement says. This is what you should do, and then they do it, right? And this happens in now avionics systems where you have very well inspected and, as requirements go, really, really good requirements. They're still really wrong or incomplete or inconsistent. So anyway, then we run more analysis and we find out that the model doesn't meet the requirements. So we change the model, or we inspect this and think about it really hard. Change the model, and we also realize that we should change the requirements. And we keep on doing this over and over and over again. And my hypothesis or assertion here is as we do this, keep checking these English language requirements, formalized requirements, models against each other. And when we find discrepancy, we think about it, and then we fix whatever is wrong. It's not necessarily the model that's wrong. Right? It might be the requirements that's wrong. It might be that the English requirements are actually right, that we formalized them poorly. Or it's oftentimes that the formalized requirements are wrong because the English language requirements are poor. So we fix the model, we fix the formalized requirements, and go back and fix the natural language requirements. And you can do this in this iterative fashion. Now that doesn't preclude doing things like testing, for example. So we make these little changes and we're changing the requirements, and now we run our verification tools, these model checkers. They're not going to find any faults anymore because the model does what the requirement said it was going to do. But if you also test these, hopefully not as much as you would have had to do if you didn't have these analysis tools, you might run it and you run some behavior down here, and this was for an Air Force talk. So the general here, he goes, that's effed up. It shouldn't have done that, right? But the verification came out okay, but he says, no, it's still effed up. You ran the testing, it shouldn't have done that. And then you look at it, you inspect it, you think, and you realize, okay, fine. The requirements are wrong here. It shouldn't have done that. And then you keep on running your analysis, and now you find another problem, and you change your model. So you keep on doing this in an iterative fashion. Right? But you're doing it in this modeling domain, not hacking, working with your code. So, does that make any sense? It does to me.
I got a question.
Yes.
So you said you don't, the notional requirements are tough. So how do you know if you've moved,
How do you know?
You probably have as the model and the formal requirements. So then the notional requirements are basically the hardware?
No, that's what it should have done. So we don't know, that's what you wanted to. So when you wrote your requirements down, you tried to capture what this
other set of formal requirements off in the...
No, they don't exist.
Someplace.
Then this is really the validation.
Otherwise, how do you know?
You don't. And that's the problem, right? So you have two. When you do verification, like we do with these model checkers, for example, verification, these are 2 words that's overloaded and they're used differently, but this is the way I like them. Verification, you always do with respect to something else. So you have your requirements, you can verify that your code meets the requirements, running all kinds of test cases compared to the requirements. Yep, everything is looking good. That doesn't mean the requirements are not wrong, right? Validation is when you want to make sure that you're actually having the right requirements, you're building the right system. So there are 2 questions. A verification is, are we building the thing right? Are we building the thing we said we were going to build? Right? Validation is, are we building the right thing? Are we building the thing that the customer really needs? Right? And really what I've been talking about here is rolling both of those in together. So you're running this verification and you find a discrepancy between your requirements and your implementation, really. Now you need to fix that. That becomes a validation activity. Well, they don't agree with each other. What should it have done? And then you try to sort that out, and then you fix either your requirements or your implementation. Then you run more analysis and you find a discrepancy and you think about it, what should it have done? Right? Now, it's quite possible that you're running into this scenario, right? That you keep on fixing these things and now they agree with each other, but it's still wrong, right? Because this is this nebulous notion of what the system should have done. This is the right thing for the system to do, which is we don't know what that is. Right? Or we might know what it is, but it's never been written down anywhere because we don't know how to do it. These two are our attempts to write down what the system should be doing. And by iteratively keep on testing, analyzing, and changing these things, my assertion is that we will move this into what is right. But there is no guarantee of this. Right? So that's a big, what did Mike Whalen, a colleague of mine, call it a swag, silly, wild-ass guess. Right? That's what we're hoping that it would do. We have no evidence of that. Right? And also, if you're doing all this kind of analysis, right, it would be nice to not have to test the bejesus out of this thing. And now the trade-off between doing analysis and doing testing, they're good at finding different kinds of problems. Right? So analysis helps you check whether they agree with each other. Right? If they don't agree with each other, you get information. Because then you get a counterexample, you can say, is this the right or the wrong thing for the system to do? And then you fix whatever needs fixing. When they start agreeing with each other, you're learning absolutely nothing more than that they agree with each other. It doesn't tell you whether it's right. Testing, on the other hand, you run it, you get a run, and you can look at it and go, yep, that's right. Get another run, you look at it, nope, that's not right. I don't care if they agree with each other or not. The execution here is not right. And then you fix it. But how to gain this, get information out of testing, which gives you some kind of information, verification, which gives you different kind of information, nobody quite knows how to sort of overlay these two on top of each other to get maximum business value. So that's a good question. So we don't know that we're going to move in here. That's just what I claim. And this is a dangerous claim to some degree, because writing down requirements, so this is typically what happened when we work with the companies trying to do this. You write down, so this was the original requirement. When the mode analyzation shall be turned on when the flight director is turned on. That was the requirement that actually was in their document. We ran the verification and it comes back and says, nope, that's not true. If you're not the, I think it's the active, if you're not the active flight director, you're just going to do whatever the other flight director tells you to do in a slave configuration. So this doesn't necessarily hold, so we have to change the requirement and say if this site is active, the mode analysis shall be turned on when the flight director is turned on, so we have to modify everything. You run the verification and it comes back and goes, no, that's not the case, because if the mode analysations are already on, we're not going to turn them on again, so if this site is active and the mode analysations are off, blah, 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 and that turns out that that's also false. Because a lot of requirements are written, the system shall do this. But there are a lot of assumptions, a lot of cases when the system shall not do that at all. You've detected an error of some sort, there's a failure mode, there's an alarm going on. There's all kinds of reasons why the system is not going to do this. And the requirements that were written never captured it. Right? These tools ruthlessly help you expose. It's quite, I think I have a guy here, really frustrating. Because it points out how bad your requirements are, right? So this iterative process turned out to be quite useful to get really, really, really good requirements. And that's how Rockwell Collins and some other companies have been able to save a lot of money, because they got the functionality right the first time. Right? And I think we've talked about that, or well, we'll get to that. In the good old days, writing good requirements was really, really important. How many of you have been involved in Agile, Scrum kinds of things nowadays? Some of you. Right? They've decided that requirements are highly overrated. And you can do other things. And we'll get to that a little briefly at the end. But writing these things down was extremely useful in terms of getting good business value. Yes, it's a boatload of work, but it really pays off later by not having any defects during testing, right? And it allowed Collins and a few other avionics companies, they're really on the forefront of this, to do other things. For example, do requirements changes coming from Boeing real late, right? What they have to do is to change the properties that you're checking. And it happened quite frequently that it turns out that their system already did this. So they change the property, rerun the verification. It goes, yep, you don't have to change your model. It already does, implements this requirement change. Or it doesn't, and they can quickly pinpoint where it is. They can fix it, rerun the analysis. They don't have to update now, 10,000 test cases that they had carefully developed to exercise certain parts of this system. They could wait with all of that until later, and then they get the code out, develop the test cases, everything works, right? So that was quite powerful. And in this, in this work we've been putzing around with these companies in the critical systems domain, I've come to the conclusion that you need all three of these, which is now not a popular argument with management because it's obnoxious enough to write requirements. What the hell are you talking about? You want us to build models and write properties and you want me to write down the same crap 3 times? Are you crazy? And yes, but it does pay off. And there was one company, a large medical device company in Minneapolis that went with this model-based approach. They were really pioneers, I would say, not necessarily in a good way. They started too early because the tools were just not good enough to do what they wanted to do. So they started probably 20, 25 years ago. And they decided that these models, they are the requirements. They were allergic to what they call double specking things. If you wrote it down in a model, they used state charts, which looks kind of like this from a company called iLogix. And they wrote everything in those state charts. They didn't write natural language requirements. So now the requirements were embedded in these models somewhere. And of course, the FDA came in and asked, where is the requirement that says that you can't pace, for a pacemaker, pace faster than 180 beats per minute? And they go, well, it's in here somewhere, right? It's over here and a little bit over here. They couldn't pinpoint. They couldn't just point to that requirement and say, yep, here's the requirement that's required from our system. So they ended up getting hammered with this. They had to actually rewrite now all natural language requirements for their pacemaker and trace that back into their models. These models are not requirements, right? So they made that mistake. Trying to write these declarative properties, this temporal logic stuff, you could technically capture your entire system using these. You're going to fail. It's going to be so wrong it's not even funny, right? But capturing some really important requirements with these properties and then double checking them with the model and having these to explain what you're actually doing gives you a really powerful set of things to work with. So that's what I've come to believe for these kinds of systems. And this notion of an iterative process, this is nothing new. Most of you probably, you're old enough to remember this, right? The spiral model, Barry Boehm's model, which is really, but on a grand scale, an iterative. You prototype, you analyze, you risk assess, you do this over and over and over again and expand your system until you have something that's workable. Right? A colleague of mine, came to the conclusion that if you look at this is a problems domain, this is the solution. You could think of this as requirements and design or architecture. We can't do all of the requirements and then we start doing our design. We write some requirements, then we think a little bit about the solution. As we're doing that, we learn more about the system, so we develop more requirements. Now we can do more of the solution, and then we keep on doing that, and eventually we have a good set of requirements and we have a good solution. But trying to come up with this, all the requirements up front, is doomed to fail. Thus, agile and all the risks with the waterfall development method for our process. Right? We just can't. It has to be an iterative way, so we learn as we go along. And this is another view of this. This is from a paper that this Steve Miller that I mentioned before wrote about how to use this and the experiences from this flight guidance project that they executed, where you really work with these different models, shall requirements and the properties that I talked about and feed this into this analysis tool and keep on fixing things until it all agrees with each other. And then, of course, the assertion now is when they all agree with each other, you've gotten it right. Worked in their case and worked in some other cases, but there's no guarantee. I would love to have some way of telling this is right. But sadly, we don't have that. All we can say is that these things agree with each other and I think it's right. Right? So any questions and concerns about this? Because this is about what I was going to say. There's a lot of work to be done here. I really believe in these techniques for a lot of critical and embedded and other kinds of systems. You can do a lot of security modeling using this also, protocols, other critical things. I wouldn't go off and try to model my website or web server or something else using these techniques, but if there are critical aspects of that you really want to get right, where the costs of getting things wrong are quite high, it's definitely something that's worth looking at. So I was going to talk about some research needs, but I think I'm going to skip that real quick and say, remember this? Use cases? Now they're not use cases anymore. They are, what do they call it in the Agile world? User stories?
No.
Pardon? Somebody said something.
I've heard user stories.
Yeah, user stories. But use cases, this is really, you have your actors, and this is a teller machine, and account holder wants to withdraw cash. That's a use case. That's something I want to achieve with my system, right? And then people write down these, so this is just a straight paragraph sort of scenario. So this is how you withdraw cash. The customer inserts the card in the ATM. The ATM accepts the card and asks the user for the PIN, if the PIN is correct, and then you describe how you withdraw cash, right? Now you can have another scenario where you have the wrong PIN, for example, or it can't read the card, or you don't have the sufficient balance, or all kinds of other reasons. This is what we would call the happy path. Everything goes well, right? But you could write more scenarios about when things go wrong. And you look at this notion of user stories. That's even more abstract than this. Then you would say, as a bank customer, I want to withdraw cash. That's your user story. Are these things requirements? What are they? What is this?
Like an interaction.
Yes, it is. This will be on the test later. It's a test case, right? This is a normal sort of good execution test case. You walk up, you insert data, it spells out exactly what should be happening in this test case with the system, right? So these scenarios that you write down, they're in essence test cases. And test cases are not requirements. They're very useful to help you illustrate what the requirements are intended to do, right? To validate your requirements, to check if your requirement has been well written. And so you write a test case for the requirement. If you can't write a test case for a requirement, it's not a requirement. Or it's really crappy requirement. Either way, you have a problem, right? So you fix it. But these are not requirements. Doesn't matter how many you have, they're test cases. Right? And if you work in the Agile world, they come up with this user story that says, as a customer, I want to withdraw cash. And then what they do is, of course, they do test-first development. So they now define a whole bunch of test cases for that user story. In essence, what they're doing is developing this. Right? They don't call it that. They call it test-first development. But in essence, that's what you're doing. You have a very vague requirement. I want to withdraw cash. You solidify that with a bunch of test cases. Right? And then you use that as a basis for development. right? And that seems to work in a lot of these agile domains, but they're not working from requirements. They're working from test cases, right? And that works sometimes, but when there are important things, the system shall never do this, shall always do that, other kinds of, that covers everything. You're not going to catch that with these test cases, right? You're going to miss a lot of failure scenarios, other kinds of things, because I don't know what your experience is, but you have the happy path, and there's probably a factor of 10 or 100 to 1 bad things as opposed to happy things, right? And you're not going to write down all these bad scenarios. You're going to write down the good ones and a couple of bad ones and then hope for the best. So I find these use cases, user stories, and all of those things, yes, they're useful to help elicit requirements, understand the requirements, but they're not requirements. And that's something that we don't want to lose track of. So if we see this as what it is, it's test cases and can be enormously useful, but it's not requirements. If you want requirements, you're going to have to go and start thinking along this line of things. And if it's really important, I think this is the way to go. Yes?
So you were talking mostly in an operational mode. What about an error handling mode and that sort of stuff? Are the requirements different from that standpoint?
No, you would put all of that in requirements. So you would have all of these requirements here, yeah. So if you see something like this, raise an alarm, shut everything down, and you could build in error, fault tolerance, all these kinds of things. This typically gets built into these requirements, built into these models. So there are projects we're doing right now that where you're interested, you build the model, and then you can say, you can put a failure model in here. So you can say, these components can fail. There's a valve or there's a switch. It can be stuck, closed, stuck, open, or just flip-flop or float or whatever, undetermined state. And you can inject these failures into your models. You can say, well, given that we only have one permanent failure of a component, do all these requirements still hold? Right, which is something you would like in a fault-tolerant system. So you can absorb single point of failures. And then you feed it into this tool and it comes back and says, yep, if you have one component failing, it still meets all the requirements. Then you up that and say, well, what about two components failing? Will I still meet my requirements? And inevitably it comes back and says no. Because if this fails and this fails, you're screwed.
Yeah.
Right, typically. But you could build a system that can absorb two simultaneous faults. So there are all kinds of things that one can do in this, with these formal frameworks, ask these kinds of questions. We're not quite there yet, but you're interested in, for example, you can say, is there any combination of failures that will exceed a failure probability of 10 to the minus 5? Right, push the button, it comes back and says, no, there is no such combination of failures that can lead to that. Or it says, no, there is, and here they are.
Well, I was thinking operationally, it's a lot easier to write the requirements. But from an error standpoint, it is often, how do you anticipate all the errors and that, the combinations and that sort of stuff? Or, one of the most interesting tests used to be ESD sorts of things, because it would put machines into modes that never intended, right? And that's where you actually learn what the machine was really doing. So.
Yeah, you should invite the guy from Honeywell, Kevin Driscoll. I don't know if you want to hear about those kinds of things. He gives a talk that he calls Murphy Was an Optimist. About just those kinds of things. And of course you do this, we're software guys and gals, so you're abstracting a lot of things away. You say my code is correct, right? That is of course modular, the processor and the hardware and the memory and the buses and all these other kinds of things that could go wrong, right? So you're always doing this with some assumptions about where it's going to be used, which is a big risk. Right, and I've seen too many places, they build models, they write down properties, they analyze it and go, it works. And then they forget about all these other things that could go wrong. So there was actually an incident that gave formal methods this kind of work a really bad name. It was, I think it was a Boeing, yes, it was a Boeing aircraft. I think it was a 787 actually, where there was a company that had worked on a part of this flight control system, and now they had, this was running in the airplane. They had the FAA out there for some of the final sort of checks that they're doing with this, and the whole cockpit just died. Right? They were turning things and just dead. Everything was just blank. That's not a good thing. And what turned out it was not a number overflow problem. That was an uncaught exception. That couldn't happen because they had proved it couldn't happen. Right? So they didn't check for this exception because they knew the code couldn't possibly throw a not a number exception, an overflow exception. And they formalized all of this. So they said, you take a number and you add that to a number, you get a number. You take a number, you multiply it with a number, you get a number. You take a number, you divide it by a number. As long as this number is not 0, you get a number back. And then they analyzed the code and they said, nope, there are no runtime errors. We can't get any not a number exceptions because there's no division by 0. They had completely and utterly forgotten that you have a fixed bit length, right? So if you get a number that's bigger than what it can handle, you get a not a number exception. They had done all their proofs in math world, which is very different than the real world. So in math world, everything worked fine. In the real world, they multiplied 2 large numbers together and got a 2 large number back, and the whole thing just died. Right? I'm pretty sure Boeing is not going to use some of these formal method techniques for the next 30 years because of that. Right? So if you use this, it's not a panacea. You need to know what the hell you're doing or you're going to shoot yourself in the foot. Right? And I have some other slides and another talk, but I mean, it's easy to screw up software engineering, right? And when you're doing testing, at least it's hard to screw up testing, right? It's easy to do it badly, but when you run your software, it does something and you can expect, at least you know it worked for that, right? To really screw up software, you need formal methods. Because you can prove all kinds of nonsense, and if you do it poorly, you have really no idea what's going on, right? So either you're really good at it or you combine it with testing as a reality check. And that's this iterative process again. So that's really all I was going to say. I don't know if it was any helpful, but I think there is promise in a lot of these things, especially in domains like medical devices, avionics, automotive, and other kinds of embedded critical domains. I think it can be enormously cost effective. So that's all I have to say. If you want to talk more about these things, you know where to find me. And thank you very much for paying attention.
Arizona, February.
Okay, if there are questions, come on down and talk to Mats.
You wanna-
If not, if you would want to pick up around your area, Mayo was very kind to let us use their facility and so forth, so, but it's obvious that we need to do our part and make sure that we take good care of the place as well. And as Dave mentioned earlier, we had planned for a machine learning sort of thing in October. That may or may not happen, but we'll have a backup plan, I guess. So plan on seeing us again in about a month. So. Okay, thank you.
I was thinking when I got tires on that.
Who's doing the interesting stuff from a commercial?